10.5 Lesson 5 Arc length and area of a surface of revolution in polar form. Our objectives for today are 1. You will understand the derivation of the integration formula for arc length of a polar graph. 2. You will be able to find the arc length of a polar graph. And 3. You'll be able to find the surface area of a surface of revolution formed by revolving a polar graph about an axis of revolution. So we will start with objective 1. You will understand the derivation of the integration formula for arc length of a polar graph. In section 7.4, we derived this definition of arc length, which is an integration formula, and you can go ahead and click on the link to view that derivation. But we started with line segments, and we approximated the length of our curve by using n line segments and using the distance formula to find the length of each line segment. And then we added the lengths of the n line segments and manipulated that sum to turn it into a Riemann sum. And then we used the mean value theorem to further manipulate the sum. And then we used the limit of the Riemann sum as the norm of the partition was approaching 0. And we were able to conclude based on the hypotheses that the limit must exist, and that gave us, by definition, this definite integral. And that's what we did in section 7.4. You have the graph of a rectangular equation, and you're looking at a particular part of the graph called an arc, and then we're finding the length of that arc. I do want to just change A and B and label that as x naught and x sub 1. But I'm not really changing anything, just changing how I'm labeling the lower and the upper limits of integration there. Then we started learning about parametric equations, and we had the same problem in section 10.3, the problem of finding arc length. The only difference was that in section 10.3, our arc is now described by a set of parametric equations on the interval from t is equal to a to t is equal to b. But we're doing the same problem, so we can start with what we had in section 7.4, and then we derived the integration formula that we used in section 10.3, and you can click on the link to see the derivation of this particular integration formula. This is how to find arc length in parametric form, and we get this formula from the one that we had in 7.4. So you would take the definite integral from t is equal to a to t is equal to b, and the integrand is the square root of the square of the derivative of f of t, and of course f of t is the parametric equation for x, plus the square of the derivative of g of t, and of course g of t is the parametric equation for y. You can also write f prime of t as dx dt, and g prime of t as dy dt. Today we're in section 10.5, and we have the same problem that we had before, but the difference is now we're in the polar plane, and we have an arc, which is an arc of a polar curve, or a polar graph. And this particular arc is traced from theta is equal to alpha to theta is equal to beta. And the problem is the same as what we had before in 7.4 and 10.3. How do we find the arc length of this particular curve? And today we're going to see how we get an integration formula to find arc length in polar form. And this particular formula will be derived from the integration formula for arc length in parametric form that we had in section 10.3. So ultimately, it can be traced back to what we had in section 7.4, and that was, of course, developed using the representative element of a line segment, the distance formula, an approximation given by a Riemann sum, and then taking the limit of the Riemann sum to get that definite integral. So let's take a look at how we can get the integration formula for arc length when you have an arc that's given by the graph of a polar equation on the interval from theta is equal to alpha to theta is equal to beta. So how will we do this? Here's how we're going to do it. We know how to convert polar equations to rectangular equations. We have these conversion equations, or the conversion equations are stated as coordinate conversion in your textbook, Theorem 10.10, and we know what they are. So we have x is equal to r times cosine theta, and y is equal to r times sine theta. Using these coordinate conversion equations, we can represent our polar equation as a set of parametric equations that you see here, x and y. And once you do that, you can go back to what we did in section 10.3, because you would now have represented our polar equation as a set of parametric equations, allowing you to use what you did in 10.3, arc length formula for a curve represented by a set of parametric equations, starting here and then simplifying to get a neat little formula that would allow you to directly find arc length of a polar curve from r is equal to f of theta, your polar equation, without having to go through converting it to a set of parametric equations. So we do the conversion for the sake of seeing how the integration formula for finding arc length in polar form is derived from the integration formula for finding arc length for a set of for a curve given by a set of parametric equations. But once you've done the derivation, you no longer need to convert your polar equation to parametric form and do this process, because you will be able to use this neat little integration formula that we will derive now and just do it directly from your polar equation, applying the formula that we're about to derive, and that would give you arc length of your polar curve. So now we're going to do what we just outlined. We'll begin by rewriting our polar equation as a set of parametric equations. So x is equal to r times cosine theta. We'll replace r with f of theta. In other words, whatever our polar equation is. And y is equal to r times sine theta. We'll replace r with f of theta, whatever our polar equation is. And if you have this problem, you know how to find arc length using the arc length formula for a curve given by a set of parametric equations from 10.3. So if we want to find the arc length of this curve given by our set of parametric equations, we need to find dx dt and square it. We need to find dy dt and square it, so that we can substitute that information into the integral. And one thing that you should realize is that this is the same problem that we're trying to work on right now. The only difference is if you have the polar equation, this would be the pole, this would be the polar axis, but you would have the same curve, and it would be described by this polar equation from theta is equal to alpha, giving you the first endpoint, to theta is equal to beta, giving you the second endpoint. So the limits of integration will be from alpha to beta. Or you can just have a and b as well. That's perfectly fine. So our next step is to go ahead and find dx dt and dy dt. So here's our parametric equation for x. And to find dx dt, you recognize that what you have here is a product, so you have to use the product rule. The derivative of the first function times the second plus the first function times the derivative of cosine, which is negative sine. And to find dy dt, you also have to use the product rule. The derivative of the first function times the second plus the first function times the derivative of sine, which is cosine. So we have found dx dt and dy dt. So now our next step is to take dx dt and square it, take dy dt and square it, because we need to write that in for dx dt squared and dy dt squared in the radicand of our integrand in the integration formula for arc length in parametric form. So how do you square dx dt? You have to do FOIL. So you have your first term here, and you have your last term here. So when you do FOIL, multiply the first terms, and you get f prime of theta squared times cosine squared theta. Multiply the last terms, and you get f of theta squared times sine squared theta. Multiply the outer terms and multiply the inner terms, and that would give you what you're basically going to multiply these two terms here twice, outer terms and inner terms, and that would give you negative 1 times f of theta times f prime of theta times sine theta times cosine theta, and you have that twice. And you're going to do the same thing to find the square of dy dt. You're going to use FOIL. So here's dy dt, and you have to square it to get dy dt squared. And to do that, you have to do FOIL. So you've got your first term, you've got your last term. So multiply the first terms, and you get f prime of theta squared times sine squared theta. Multiply the last terms, and you get f of theta squared times cosine squared theta. And then multiply the outer and the inner terms, which will basically give you the product of these two terms twice. And that would be right here. You have it twice. You have f of theta times f prime of theta times sine times cosine. And you have that twice. So now, as a part of the integration formula for finding arc length in parametric form, what do? You're going to add the square of dx dt and dy dt. That's a part of the integrand. It is the radicand in the integrand of the integration formula for arc length in parametric form. Now, something nice happens when you add dx dt squared and dy dt squared. You'll notice that when you do the addition here, you'll notice that these two terms here will add to give you 0. And so will these two terms. They will add to give you 0 as well. So what are you left with? So you're just going to be left with f prime of theta squared cosine squared theta plus f prime of theta squared sine squared theta. And let me write that here. F prime of theta squared cosine squared theta plus f prime of theta squared sine squared theta. And of course, you will notice that these two terms have a common factor of f prime of theta squared, so you can factor it out. And when you do that, you get f prime of theta squared times cosine squared theta plus sine squared theta. And then you have this plus sign, and what you have here is coming from the sum of these two terms from dx dt squared and dy dt squared. And they also have a common factor of f of theta squared. So when you factor that out, from the first term you'd be left with sine squared theta, and from the second term you'd be left with cosine squared theta. So that's where that comes from. So now, what are we going to do? We're going to simplify further. Cosine squared theta plus sine squared theta is 1. That's a Pythagorean identity. Same here. So you are just left with f prime of theta squared times 1, which is just f prime of theta squared, plus f of theta squared times 1, which is just f of theta squared. And that is from A to B. Now, you can also say from alpha to beta. That's okay, because it's talking about the same starting point and the same ending point on the arc, regardless of whether the arc is represented in polar form or in parametric form. So the last thing that I'm going to do is just switch the order of these two terms in the radicand to make it fit the form that is stated as a theorem in our textbook. And what we've done is we have derived the integration formula for finding arc length when you have a curve represented by a polar equation. And the way we did that was we rewrote our polar equation in parametric form and started with the integration formula for finding arc length in parametric form, went through this process to come up with this new result, which will allow us to find arc length from a polar equation directly without having to do the process that we just went through. We only had to do this one time to get this result. So now let's go ahead and use it to look at an example for finding arc length of a polar curve. So this is Theorem 10.14, arc length of a polar curve. Let f be a function whose derivative is continuous on an interval from alpha to beta. The length of the graph of the polar equation, r is equal to f of theta, from theta is equal to alpha to theta is equal to beta, is given by this definite integral, and of course we saw its derivation just now. So f of theta is your polar equation. So what you need to do is you need to, for the integrand, you will have the square root of the square of your polar equation plus the square of the derivative of the polar equation with respect to theta, or dr d theta, as you see written here in equivalent form. So you take your polar equation and square it. You take the derivative of your polar equation with respect to theta and you square it. You have to add those two and then take the square root. That's your integrand, and the limits of integration are from alpha to beta. Let's go ahead and take a look at example 4 from the textbook. So here's example 4. Find the length of the arc from theta is equal to 0 to theta is equal to 2 pi for the cardioid given by r is equal to 2 minus 2 times cosine theta. That's a 2 pi there. And if you look at the graph of the polar equation, you see this cardioid. When theta is equal to 0, cosine of 0 is 1. 2 times 1 is 2, and 2 minus 2 is 0. So you have this point, r theta, where r is 0 and theta is 0. When theta is equal to pi, you have cosine of pi, which is 0. 2 times 0 is 0, and 2 minus 0 is 2. And you have this point, r theta, where r is 2 and theta is pi over 2. When theta is equal to pi, cosine of pi is negative 1. 2 times negative 1 is negative 2. And 2 minus negative 2 is 4. So when theta is equal to pi, you have this point with polar coordinates r theta, where r is 4 and theta is pi. And then when theta is equal to 3 pi over 2, you have cosine of 3 pi over 2 is 0, 2 times 0 is 0, and 2 minus 0 is 2. So you have this point with polar coordinates r theta, where r is 2 and theta is 3 pi over 2. And when theta is equal to 2 pi, you complete the cardioid. So substitute 2 pi for theta. Cosine of 2 pi is 1. 2 times 1 is 2. 2 minus 2 is 0. And you are once again at the pole. But this time the coordinates will be 0, 2 pi. So that's the cardioid. And of course, as we go from theta is equal to 0 to theta is equal to 2 pi, this is how the cardioid is being traced, as you can see me showing you with gold. And we want to find the length of this arc, and to do so we're going to use this integration formula. And as you can see from the integration formula, we need to do a couple of things. We need to square f of theta, and we need to find the derivative of f of theta and square the derivative, so we can substitute those expressions into the radicand in the integrand. So let's go ahead and take a look at what that would be like. So squaring f of theta, how do you do that? You have to use FOIL. So squaring f of theta is just doing 2 minus 2 cosine theta and squaring it. So that's going to give you 2 minus 2 cosine theta times 2 minus 2 cosine theta. So when you multiply the first terms, you get 4. When you multiply the outer terms, you get negative 4 cosine theta. When you multiply the inner terms, you get negative 4 cosine theta. And when you multiply the last terms, you get 4 cosine squared theta. And of course, you can combine the like terms and have 4 minus 8 times cosine theta plus 4 cosine squared theta. Now you need to find f prime of theta. So f prime of theta is going to be the derivative with respect to theta of your polar equation. So the derivative of the constant term is 0, and the derivative of the non-constant term would be, the derivative of cosine is negative sine, so you have minus negative, which would be positive, so you're going to have 2 sine theta for f prime of theta, and then you have to square it. That's a part of the radicand of the integrand. So when you square it, you're just going to get 4 sine squared theta. So the next thing that you need to do is, of course, go ahead and substitute this into our integration formula. So when you do that, you're going to have the definite integral. So arc length is given by the definite integral from alpha to beta, from 0 to 2 pi, to complete the cardioid that you see in the graph. And then the radicand, the integrand will be the square root of, and in the radicand we're going to have f of theta squared, which is 4 minus 8 times cosine theta plus 4 cosine squared theta plus f prime of theta squared, which is right here. So we have plus 4 sine squared theta, and of course you need to write d theta. I'm trying to fit it in here, d theta. Okay, so that's a d theta right there. So now we see what the integral is that will give us our arc length. And let's go ahead and work with that to evaluate it. So how do you evaluate this definite integral? You're just going to go one step at a time, doing what you can to simplify the integrand. Now you can simplify the radicand of the integrand as follows. You can write 4 minus 8 cosine theta, and for these two terms you can see that they have a common factor of 4. So you can factor out 4, and from the first term you'd be left with cosine squared theta, and from the second term you'd be left with sine squared theta. And that's good news, because we know from the Pythagorean identity that cosine squared theta plus sine squared theta is equal to 1. So what you really have is just 4 times 1, and then you have 4 plus 4, which will give you 8. So now we can write the definite integral from 0 to 2 pi, and we have the square root of 8 minus 8 times cosine theta. So what do you do next? Well, here's one thing that you can do. you can factor out an 8 from each term in the radicand. And when you do that, you'll have 1 minus cosine theta as a factor in the radicand, and the other factor would be 8. And what can you do here? You can use a property of nth roots and write this as the square root of 8 times the square root of 1 minus cosine theta. And you can further factor 8 as 4 times 2. 4 times 2 is 8. And you have the square root of a product, and you can write that as a product of the square roots. And the square root of 4 is 2. And of course, that's a constant, so you can factor it out of the integral, and you will have 2 times the square root of 2 times the definite integral from 0 to 2 pi. But now you still have to figure out how you're going to integrate, and here's one way to do it. You can use a power-reducing formula to rewrite 1 minus cosine theta. So let's see how we will do that. When you look at the power-reducing formulas, you see 1 minus cosine of 2u over 2, and that's equal to sine squared u. If I manipulate that by multiplying both sides of the power-reducing formula by 2, I would get 2 times sine squared u is equal to 1 minus cosine of 2u. And what you have here is very much like 1 minus cosine of 2u, but I don't have 2 theta. But here's what you can do. Although you don't have 2 theta, you have theta, but you can write theta as 2 times 1/2 theta. 2 times 1/2 theta is theta, but now it is exactly in the form 1 minus cosine of 2 times an angle u. And our angle would be 1/2 theta. So now we're able to make the following substitution to further simplify our integrand. We have 2 times the square root of 2 times the definite integral from 0 to 2 pi. And now we can write the square root of 1 minus cosine of 2u is 2 times sine squared u. So now we can write 2 times sine squared, and our angle u is 1/2 theta, or theta over 2. So that's how we make the substitution using the power-reducing formula. But you're not quite done. You still need to do something here. You might be thinking, okay, can I cancel the squaring here with the square root? You do have to do a little bit of thinking before you do that. So let's go ahead and discuss that briefly, and then we will go ahead and do the cancellation. Preliminary steps are to recognize that you have a product here. So you have the square root of a product, so you can write the square root of 2. So you can write the square root of 2 times the square root of sine squared of theta over 2. And of course, this square root of 2 is a constant, so you can factor it out and multiply it to 2 times the square root of 2. So 2 times the square root of 2 multiplied by square root of 2 is 2 times 2, which is just 4. So that gives us just 4 times the definite integral from 0 to 2 pi of the square root of sine squared of theta over 2. Now you do have to, before canceling the squaring and the square root, you need to keep this in mind. The interval for theta is from 0 to 2 pi. But now the argument is theta over 2. So when you divide 0 by 2, you get 0. When you divide 2 pi by 2, you get pi. So on the interval from 0 to pi, sine is positive. So you will have sine of theta over 2 be positive on this interval of integration. And when you square a positive quantity and take the square root, it is as if you just have the original quantity and didn't do anything with it. And that is why you can cancel the squaring and the square root to give you just sine of theta over 2. And now we have it simplified enough so that we can go ahead and integrate it. So let's go ahead and integrate, and then we will finish the problem and find the length of our arc. How do you find an antiderivative of sine of theta over 2? An antiderivative of sine would be negative cosine. The derivative of cosine is negative sine. So antiderivative of sine is negative cosine. But you do have to be careful when you write negative cosine of theta over 2, and then you take the derivative of this, you would be using the chain rule and multiplying by the derivative of the inside function, which will give you a factor of 1/2. But you don't want that factor of 1/2, so you compensate by multiplying by 2. And when you do that, this is what you have for your antiderivative. And we're going to go ahead and evaluate. So we have 4 times negative 2 times cosine of theta over 2, evaluated at 2 pi and 0 and subtracting. So what is, when you substitute 2 pi for theta, 2 pi divided by 2 is 1 pi. Cosine of pi is negative 1. Negative 2 times negative 1 is positive 2, minus, when you substitute 0 for theta, 0 divided by 2 is 0. Cosine of 0 is 1. Negative 2 times 1 is negative 2, so you have minus negative 2. So that's equal to 4 times 2 minus negative 2 is 4. 4 times 4 is 16. So what is the arc length of our polar curve? It is going to be 16 units. So 16 units is the length of this polar curve as theta goes from 0 to 2 pi. So we just did objective 2. You will be able to find the arc length of a polar graph. We're going to complete the lesson by looking at objective 3. You'll be able to find the surface area of a surface of revolution formed by revolving a polar graph about an axis of revolution. So for the third objective, we want to find the surface area of a surface of revolution formed by revolving a polar graph about an axis of revolution. So let's take a look at what that means. So again, we have our polar coordinate plane with the pole here and the polar axis. And if we have a curve defined by r is equal to f of theta, from theta is equal to alpha, giving us our starting point, to theta is equal to beta, giving us our ending point, and we revolve this arc about either the polar axis or perhaps the radial line theta is equal to pi over 2, we can form a surface of revolution. And the question that we have is, how can we find the area of such a surface of revolution? This problem is the same problem that we did in section 7.4 and section 10.3. The only difference was that in section 7.4 we had an arc of a graph that was given by a rectangular equation, and in section 10.3 we had an arc of a graph that was given by a set of parametric equations. In each of those cases, we could have taken the arc and revolved it about either the x-axis or the y-axis. To obtain a surface of revolution. So in section 7.4, the graph was described by a rectangular equation. And in section 7.4, we saw that this was the integration formula that would give us the length of the arc. And then if you take that arc and revolve it, you get a surface of revolution, and this was the integration formula that would give us the area of the surface of revolution. And you can click on the link to see how we came up with this integration formula, starting with the pre-calculus formula for the lateral surface area of a frustum of a right circular cone. So we used the representative element frustum of a right circular cone to come up with first an approximation for the surface area, and then we wrote a Riemann sum that gave us the approximation, and we took the limit of the Riemann sum as the norm of the partition approached 0, and we arrived at this integration formula in section 7.4. Important to note in this particular integration formula is r of x, and that tells us the distance from the axis of revolution to a point on the arc that is being revolved. And so if the axis of revolution is the x-axis, r of x would be the y-coordinate of a point on the curve. Or if the axis of revolution was the y-axis, r of x would be the x-coordinate of a point on the curve. Also important to note is this part of the integrand. And you will see that that is the same as the integrand from the integration formula for arc length. And the reason for that is because when we used the distance formula, when we approximated the length of the arc using line segments, and then used the distance formula, and then wrote a Riemann sum, and then took the limit of the Riemann sum to get this definite integral. That's what we did for arc length. And we also used line segments to derive this integration formula. And we took a line segment and revolved it about an axis of revolution to obtain a frustum of a right circular cone. And so this particular factor in the integrand that I circled in blue is from a line segment that is being revolved about an axis of revolution to give us a frustum of a right circular cone. And that's why you see that both in arc length and the area of a surface of revolution. And we talked about r of x, and if you refer to the video that I asked you to click on, the link that was provided earlier, it explains to you where this particular factor comes from the pre-calculus representative element and the formula for the surface area of a frustum of a right circular cone, the lateral surface area. So you can refer to that for more information. But what I want to focus on now is this. Certain things that carry over whether we're doing the problem in rectangular, parametric, or polar form. So you will see that in parametric form, here we have the integration formula for arc length, and in parametric form, in the integration formulas for the area of a surface of revolution, you see this factor, which is the same as the integrand from the integration formula for arc length. And then when you compare what you have here to the integration formulas for the area of a surface of revolution when you have an arc given by a rectangular equation, you will see that you have 2 pi, and that is coming from the pre-calculus formula for the lateral surface area of a frustum of a right circular cone. All of this is coming from that pre-calculus formula, but it carries over whether we're doing the problem in rectangular form or parametric form or polar form. So in rectangular form, you had r of x. And what was r of x? The distance from the axis of revolution to a point on the arc that is being revolved. You have that in parametric form and polar form as well. So in the first formula here, I will go ahead and label this 1. The axis of revolution is the x-axis. And in the second formula here, I'll label this 2. The axis of revolution is the y-axis. And this particular factor, it tells us the distance from the axis of revolution to a point on the curve. And if you look at our diagram on the left side of the screen in the middle, you will have a point on the arc described by the set of parametric equations, and the coordinates of this point, of course, are x comma y, but f of t is the x coordinate, and g of t is the y coordinate. So that's what we have here. We have f of t for the x coordinate, and we have, let me write it in a different color here, g of t for the y coordinate. And of course, this factor in the integrand, g of t, why do we have that? Because we need to have there the distance from the axis of revolution to a point on the curve. And g of t is the y coordinate, and that is the distance from the x-axis to a point on the curve. And in the second formula, where the axis of revolution is the y-axis, why do we have f of t here? Because again, that is coming from r of x, from the integration formula for the surface area of a surface of revolution in rectangular form. And that r of x factor gave us the distance from the axis of revolution to a point on the curve. So if we're doing the problem in parametric form and the axis of revolution is the y-axis, we should have f of t there, because f of t is the x-coordinate of a point on the curve, and that x-coordinate will tell us the distance from the axis of revolution, the y-axis, to a point on the curve. And in the same way, we can take a look at what we have for finding the surface area of a surface of revolution in polar form. So you will notice again that you have this integrand in the formula for arc length when you have an arc given by a polar graph, and you will see that factor as a part of the integrand in the integration formula for the surface area of a surface of revolution in polar form. And just like you had in rectangular form the factor of 2 pi, you have that here in polar form as well. So where is this coming from? It is coming from r of x when we looked at the problem in rectangular form, and it is telling us the distance from the axis of revolution to a point on the arc that is being revolved. So when we look at the two formulas for polar form, for the area of a surface of revolution, in the first case, the axis of revolution is the polar axis. And in the second case, the axis of revolution is the radial line, theta is equal to pi over 2, which would be equivalent to the x and the y axes if we were doing this in the Cartesian plane. So if you have a polar equation, r is equal to f of theta, and you wanted to convert that into a set of parametric equations, what would you do? You're going to use x is equal to r times cosine theta, and y is equal to r times sine theta. And that allows you to write the coordinates of a point on your polar curve using rectangular coordinates. So the x and the y coordinates would be r, which is f of theta times cosine theta, comma r sine theta. R is f of theta times sine theta. So f of theta times sine theta, what is that? That would be the y coordinate if we were doing rectangular coordinates. And that would tell us the distance a point on the curve is from the x-axis or the polar axis. And that's why we have f of theta times sine theta here, because it is coming from r of x of the integration formula for surface area in rectangular form, which gives us, of course, the distance from the axis of revolution to a point on the arc that is being revolved about the axis of revolution. And if you have revolution about the line theta is equal to pi over 2, we of course have f of theta times cosine theta, because that would be the x coordinate of the point, and that would tell us the distance the point on the curve is from the y-axis, or the radial line theta is equal to pi over 2. So that should help you see how all of this is connected. And now we're ready to conclude our lesson by looking at an example for finding the area of a surface of revolution in polar form. We'll take a look at example 5 from the textbook. We'll be using Theorem 10.15 to find the area of a surface of revolution in polar form. Let f be a function whose derivative is continuous on an interval from alpha to beta. The area of the surface formed by revolving the graph of r is equal to f of theta from theta is equal to alpha to theta is equal to beta about the indicated axis of revolution. If you have the polar axis of revolution, here's the integration formula, and of course this is telling us the distance from the polar axis to a point on the curve. And if you're revolving about the radial line theta is equal to pi over 2, here's the integration formula, and of course this factor is giving us the distance from the axis of revolution to a point on the polar curve. Example 5, finding the area of a surface of revolution. Find the area of the surface formed by revolving the circle given by r is equal to f of theta, which is equal to cosine theta, about the line theta is equal to pi over 2, which is over here, as shown in the figure. So we want to take the circle and revolve it about the line theta is equal to pi over 2. And when we do that, this is the surface that we get. It is called a pinched torus. So we need to begin by writing an integral that would give us the surface area of the surface of revolution. And because we're taking our polar curve and revolving about the line theta is equal to pi over 2, we're going to use this integration formula. And of course this factor here would give us the distance from the axis of revolution to a point on our polar curve. And if you were to write your polar equation as a set of parametric equations, this would give you the x coordinate of a point on the polar curve, because you have r cosine theta, or f of theta cosine theta for x, and r sine theta, or f of theta sine theta for y. And this factor is giving us the distance from the axis of revolution to a point on the curve. The other thing to consider is, of course, what should the limits of integration be? So to determine that, you need to read the problem again. It says, find the area of the surface formed by revolving the circle given by this polar equation about the line theta is equal to pi over 2 as shown in the figure. So you need to figure out for what values of theta will the entire circle be traced out. And if you start with theta is equal to 0, cosine of 0 is 1, so r will be equal to 1, and you get this point with polar coordinates, r theta, where r is 1 and theta is 0. And if you use theta is equal to pi over 2, cosine of pi over 2 is 0, so r will be 0 when theta is pi over 2, and you will get this point, r is 0 and theta is pi over 2. And in fact, when theta is pi, cosine of pi is negative 1, so r will be equal to negative 1, and you will once again be here, where r is negative 1, and the angle of rotation from the polar axis is theta. So because r is negative 1, this is the terminal side of the angle measuring theta radians, but because r is negative 1, you plot a point on the opposite ray from the terminal side of the angle to get the same point that we started with. In other words, the important thing for you to get out of what we just looked at is that the complete circle is traced as we go from theta is equal to 0 to theta is equal to pi. And since we are revolving the circle about the axis of revolution, our limits of integration should be from 0 to pi, because that's the interval for theta on which the entire circle is traced. And now we're going to revolve it about the axis of revolution to get this surface of revolution, and here is the definite integral you write that would give you the area of this surface of revolution. So you're going to write S is equal to 2 pi times the definite integral from 0 to pi, and you are going to write f of theta times cosine theta, and of course f of theta is cosine theta, so you have cosine theta times cosine theta, which is cosine squared theta, and then you have the square root of f of theta squared. F of theta is cosine theta, so cosine theta squared would be cosine squared theta plus f prime of theta squared. So what is f prime of theta? F prime of theta is the derivative of cosine is negative sine. And if you have f prime of theta and you square it, you're going to have sine squared theta. So you're going to have plus sine squared theta, and that's integration with respect to theta. So the next step is really easy. If you look at the radicand here, you have cosine squared theta plus sine squared theta. So you can simplify by just writing that as 1. So you have 2 pi times the definite integral from 0 to pi cosine squared theta times the square root of 1, which is just 1. So this is what we have. And on the next page, we're going to take a look at how we can evaluate this definite integral to get the area of this surface of revolution. So to complete the problem, we need to use the fundamental theorem of calculus. We need to find an antiderivative of the integrand and evaluate at the upper and lower limits of integration, but we can't do it the way the integrand is presently written. So we have to rewrite the integrand using a trig identity. A power-reducing formula will help us. So if you have cosine squared u, that is equivalent to 1 plus cosine of twice the angle u over 2. So our angle u is theta, so we can now write the surface area is equal to 2 pi times the definite integral from 0 to pi. Using the power-reducing formula, I may write 1 plus cosine of twice the angle, 2 theta, all of that over 2. And we have integration with respect to theta. Now what you have here is a factor of 2 in the denominator, which of course you can see as 1/2 times 1 plus cosine of 2 theta, and you can factor out that 1/2, and when you factor out that 1/2, you will have 2 times 1/2 is 1, and that will give you pi times the definite integral from 0 to pi of 1 plus cosine of 2 theta d theta. And now the integrand is in a form that would allow me to find an antiderivative easily, allowing me to use the fundamental theorem of calculus. So an antiderivative of 1 with respect to theta would be theta, because when you differentiate theta with respect to theta, you get 1. An antiderivative of cosine is sine. The derivative of sine is cosine, so you have plus sine of 2 theta, but you need to have an adjustment, because if you have the derivative of sine of 2 theta, you'll be using the chain rule, and you'll actually get 2 times cosine of 2 theta, but you don't want 2 times cosine of 2 theta, you want 1 times cosine of 2 theta, so you need to divide by 2. And now we have our antiderivative, so we're going to evaluate our antiderivative at pi and at 0 and subtract, and of course don't forget to multiply by this factor of pi. So we have pi times, so we replace theta with pi, plus we replace theta here with pi, so we have sine of 2 pi, which is 0. 0 over 2 is 0. Minus, we will now evaluate our antiderivative at the lower limit of integration. Replace theta with 0, plus replace theta here with 0. Sine of 0 is 0. 0 over 2 is 0. So that gives us pi times pi, or pi squared, square units. And what is this? It is the area of the surface formed by revolving the circle given by f of theta is equal to cosine theta about the radial line theta is equal to pi over 2. It is the area of this surface of revolution. It is the surface area of this surface of revolution. So in this lesson we looked at 3 objectives. We understood the derivation of the integration formula for arc length of a polar graph. We were able to find arc length of a polar graph. And before we looked at objective 3, we actually looked at relationships between the different integration formulas that we've been using for arc length and area of a surface of revolution in rectangular, parametric, and polar forms. And then we used the integration formula for finding the area of a surface, the surface area of a surface of revolution in polar form to do a problem. We were able to find the surface area of a surface of revolution formed by revolving a polar graph about an axis of revolution.